Hi, my name is Nicholas Wiley, and today we're going to be finding the maximum angular velocity for a cup filled with liquid. So the first thing I like to do with any video like this is I like to describe our system, draw a picture, and then talk about what we need to do to get from point A to point B. So let's start with what we know. What we know is that we have some cup right here. You can see that, just making sure. What this is going to be filled to is a certain height, h naught. The height of our cup is going to be big H, we'll call it. So that's going to be a limiting factor, very important in a bit. What we're going to do is we're going to spin that some velocity that we will call W, or angular velocity. And what's going to happen is we are going to get some sort of parabola shape, as you can see right here. It's a little glary with the lights, but either way. So what we're going to get is we're going to get this shape right here. It's almost like a vortex. If you've ever, for example, you ever have a bottle and then you spin it really fast and it sort of makes a vortex, the liquid hugs the edge of the bottle, you could say, in a way. Either way, what's going to happen is that the liquid is going to be it's going to look like this afterwards. Sorry, not the best with words. So what we can do with this system, we can draw a couple lines that are going to become important to us later. So what we have right here, we're going to call from this h naught level down to the vertex of our parabola-esque shape. We're going to call that the depression level. Believe that's all we need for that right now. Yes, so basically what we're going to want to do is we're going to want to balance the volumes of these cups based off of certain properties, so that in the end we're going to have this strip right here, from the top of H naught down to D right here. We're going to have both of these. This volume right here is going to be equal to this volume right here. That's going to be our goal, and then there's going to be some sort of corresponding angular velocity for that. Getting too ahead of myself though, so let's start with how we're going to get from point A to point B. We need some equations, we need some relationships. First and foremost, I believe we've used this once or twice now. We're going to use the basic equation for static fluids, which is going to be the differential change in pressure over the differential change in position. It's going to be equal to rho density of the fluid multiplied by A. So looking at this, there's not a lot that we can do right now. We have this pressure term, which we're going to eliminate, as pressure isn't really in the question that we were asked. We're mainly just talking about equating volumes, angular velocities, and heights. Pressure is a big thing, so what we need to realize is that's going to be one of our driving forces, is getting rid of that pressure value through cancellations. What we also have is we have this differential change in position z. Now, for this specific scenario, our change in position for our fluid is simply going to be from this r outwards. And why is that? Well, when we're talking about some angular velocity, what the cup will typically do is it'll act upon, the surface will act inwards so that it's not spewing out tangentially. What the fluid is doing is it's actually acting in the opposite direction, causing this to have that shape, that parabolic shape. So, but how is that going to be changing? What's that differential position? It's going to be the change in radius. As you go outwards, as you go outwards with radius, how is it changing? So the differential change in pressure with respect to position, which is going to be radius. Hopefully that made sense. Now what else do we have? We have acceleration. Now we have centripetal or angular velocity, but we don't have anything about the just normal acceleration. We don't have any acceleration in this. So what can we do? Well, one thing that we do know is that centripetal acceleration is going to be equal to radius multiplied by angular velocity squared. Now, how do we know this? There is some sort of, you could say, derivation that we will do. Well, actually, yes, it is a derivation. So what we could do, excuse me, so we could draw a system like this. We have this, and say we're accelerating along this. We're going to get to a point x comma y. What's our position going to be equal to? It's going to be equal to r cosine theta. Then we have y is going to be equal to r sine theta. And what is theta going to be? It's going to be our angular velocity, w, with respect to time. So this is going to become angular velocity multiplied by time. Practically what we do is we would derive both of these twice to get the second derivative, and then it'd become a vector. What do you call it? A vector resolution is what we would do. And pretty much what we'd end up with is we'd get cosine squared sine squared. We know our equation, cosine squared sine squared equals 1. Pretty much all of that will cancel out, and what we're going to end up is this equation right here. Just a quick aside, I thought it was pretty interesting. Thought I'd talk about it. But either way, so we know that this is going to be our centripetal acceleration, so let's plug that right in. So we're going to have dp over dr is going to be equal to rho multiplied by r, radius, and the centripetal or angular velocity squared. Okay, so what can we do with this? Well, what we can do pretty easily is we can just integrate. Since we have two different differential terms, what we can do is we can integrate. So let's do that real quick. We're going to integrate the differential pressure, and then we're going to pull out the rho and the r, and we're going to integrate this r right here with respect to dr. We'll just move that over. What are our bounds going to be? Well, we have a known pressure, which I will get to in a second. So from P1 to P, then a known radius up to a radius that is unknown for us. Okay, what can we do with this? Well, we just plug and chug. We'll get right into it. So we're going to have pressure minus initial pressure. Known pressure is going to be equal to rho times r. No. Sorry about that. I was going a little bit too quick for my own good. This is going to be outside. It's going to be our angular velocity. Because that's not changing. What we're changing is radius right here. That's my bad. So we're going to have rho multiplied by our angular velocity squared. And what we're going to have is, real quick, we're going to put this all over 2, actually. It'll be easier. Put that all over 2 because we have this r term here. It's going to be 1/2 r squared evaluated from these two. So it'll be r minus r1 squared over 2. Now, some important assumptions that we need to make. First and foremost is the pressure, the known pressure. So this known pressure is going to be at the surface of our fluid, and one of the assumptions that we're going to make is that the pressure at the surface is going to be equal to 0. So we'll just give that a big cross. Another assumption that, well, not really an assumption, but the initial radius is going to be the radius at the middle, and we are going to call r equal to 0 there, as it is in the center. So that will also cancel out. What I will do is I will write this up here carefully. P is going to be equal to rho density of our fluid multiplied by the angular velocity squared multiplied by our radius squared all over 2. Yes, that's correct. Okay. Second guessing myself. So what are we going to do now? Well, another thing that we know about pressure is when we come over here, wander on over here, at this given radius r, we have a certain pressure. So we're going to say that this is r. Now this is going to be at some height h. So what we can do is we can relate radius with height, because that's where the point that we're going to be at is right here. So at some depth h, and that pressure is not going to be equal to 0, so that's going to have some value. Something that we know is that our pressure is going to be equal to, in addition to this pressure, so forget about this for now, pressure is going to be equal to rho times g times h, something that we've known. So what we can do is we can simply do some substitutions, and what this is going to do is it's going to get rid of that p term for us, that pressure, which is no longer going to be important for us. It was mainly used as a way to bridge different, bridge our radius and bridge our height. Either way, we cancel out the densities, erase the p while we're at it, we don't need that anymore. And what are we left with? We're going to want to isolate h. H is going to be equal to, I wish I could write that. Actually, I'll write that right down here. Let me get on my, can you still see me? Yes. So h, our height is going to be equal to our angular velocity squared multiplied by our radius squared over 2g. Okay, now we're getting somewhere. Throw that over here. Now, when looking at these systems, like I mentioned earlier, what we're going to want to do is we're going to want to balance, pretty much make our volumes equal. So what we know already is that these two right here, I'm going to try and explain this better. I tried to explain a little bit earlier. But so what we have is we have this area and this area right here, the volume. So the volume right in here is going to be equal to this volume right here. And why is that? Because they're both at the same fluid level and there is no disturbances, there is no interference from the parabolic motion that is being caused by the angular rotation and velocity. So these are going to be equal. These are not going to be a big deal for us right now. What's going to be a big deal for us, it's going to be everything above that. So pretty much from H naught to minus D, so this area right here, I guess H naught to D, sorry, I'm getting a little caught up in my own words. So this area right here, what we're going to want to do is we're going to balance that volume with what is this whole area right here, this whole volume right here. Now why is that? It's because the liquid needs to be preserved. You can't gain or lose any liquid if we're staying inside of the cup at this level, H right here on both sides. So we're going to want to balance the volumes, and what we can do is we can relate those two volumes because they are equal. So let's go ahead and do that. Let's draw a quick overhead of this. Of both, actually. Not the greatest looking circles, but we try. So again, what we're looking for is we're looking for this section right here. Now, when we're looking at this, we have both of these have some middle point right there. This whole thing is going to be shaded because it is flat. And what is going to be the surface area of our liquid at this point is going to be pi big R squared. We're going to call this from the center all the way to the edge, that's going to be big R, just as though that is H. Now, what are we going to be multiplying? As I've said earlier, we're not looking for this whole thing now. We're looking for this and these right here. Why is that? Again, because these two are going to be equal. Okay, so what do we have next? Oh, we're going to multiply that by the depth. This part right here, because that's going to be this area that we're talking about, that volumetric balance. So then we're going to come over here. I'm actually going to sit on my bed, get comfy for a second. So when we're looking at this one, it's not as easy because we have this parabolic shape. So what can we do? What we're going to do is we're going to take bands of certain thickness. That is really not good. Bands of some certain thickness, which we are going to call dr. What we're going to want to do is we're going to want to integrate those across the entire parabola. So imagine this is 3D. There's a ring, and we're just going to keep going around until we get to the edge, until our thickness has reached the edge. So what's that going to be? Well, what we know is that this band right here is going to have a, a circumference, a perimeter of 2 pi r, and what we're going to do is we're going to multiply that by dr. Okay, and then what we need to do as well is we need to multiply by this variable right here, this h that we had for this certain r, we have that certain h. Okay, now what we can do is we can start plugging and chugging again. We're going to leave this down here. So what we have is we have pi big R squared multiplied by the depth is going to be equal to 2 pi times r, little r, multiplied by dr, multiplied by h. Now what we're actually going to do is we're going to plug in this h right here that we got earlier. So let's just do that right now. So I'll just add a little parentheses, and then we'll do the cancellation in a second. So we're going to have rho squared r squared over 2g. Okay. So let's go ahead and start doing that. Well, we have pi. Do we have anything else? Well, we have r cubed here. Let's just get to this. R squared d is going to be equal to 2 angular velocity squared. I guess these 2's will cancel out. So we'll just say angular velocity squared over g, I believe. I think that should be good. Because these 2's are going to cancel out. The g is going to be left, r squared d. Then we're going to be left with integral r cubed dr. Okay, we're definitely getting somewhere, as you can see. So what are our bounds of integration going to be for this? I believe, okay. So when we're talking about balancing our volumes, we're going to be going from this 0 point right here all the way to the final radius, big R. So let's go ahead and do that. That's going to be our bounds for this. Because we're trying to talk about from here until the very edge, we're not talking about these small chunks anymore. We're talking about from 0 to the end of our cup, the internals of our cup. It's going to be from 0 to R right there. And what this is going to become, real quick, let's just draw. I'm going to draw a little, I'll put a little box right here. So that's going to be R to the 4th over 4. And then what we're going to do is we're going to replace that with big R. Okay, so we're going to be left with, cross this out. This becomes R squared over 4. So we're going to have the depression, or the depth, is going to be equal to angular velocity squared, our outer radius squared, or our total radius squared, if you'd rather, over 4g. And now we're really getting somewhere. So I'm going to put that down here. It's going to be equal to that squared, big R squared, over 4g. Okay. Now we're really getting somewhere. So as I've mentioned before, what we're trying to do is we're trying to find this whole area right here, but we also need to consider down here. So let's think about this real quick. So what we have is we have the total height. Now what is that going to be equal to? Let's consider this. So we're going to have h naught minus d. That's going to be equal to this area down here. Right? That's going to be, that should be correct, because when you have this whole area right here, subtracting this area, you're going to be left with this down here. So that's going to be accounting for that aspect of the height. What are we left with? Well, what we're going to be left with is, since we're going to be in terms of r, what we're going to want is this h to go all the way up and down. So what we're going to do is we're going to add little h of this side. Because again, what we want is we want this height to be as close to the top as it can be without spilling, so do all the way up to our maximum height. Okay, and now I believe that we're good to go. Yeah, so what we're going to have is we're going to have h is going to be equal to h naught minus d rho squared r squared. I don't know why I keep saying rho squared, by the way. What I mean is the angular velocity squared, just w squared. And then our outer radius, or our total radius squared, going to be over 4g. What we're going to do is we're going to add this h value. Important thing I kind of made a point about, but I didn't really. So what we have right here is we have this height right here, this little h. And what I was saying is that you have to subtract d from this h naught, and what we're going to be left is we're going to encompass all of this volume right here, right? All of this height. And then what we're going to want to do is we're going to want to find the height so that it gets all the way up to here, okay? Because that is our limiting expression. That's what we're doing. We're putting things in terms of our limiting expression. So what we want is we want that h to be the rest of the height, so that it gets all the way up to the edge without just barely going over to the very maximum. So in addition, what we're going to have to do to get to that maximum height is we're going to have to be at the maximum radius. So this is going to become big R squared for our little h term, which did have the lowercase r before, as we were talking about this sort of radius here, but now we're going all the way through. Okay, so now what we do is we just, after explaining that, we plug in h, angular velocity squared, total radius squared over 2g. Okay, so now we can do a little bit of reorganizing, but something that you should know is fractions is basically what we have. Try and do this as light as possible with having you able to see it. I don't know if you can see that. So what we have is we have these two terms right here. They're the exact same. So pretty much that makes them equal to 1. If you like to think about it, so we're going to have subtracting 1/4, positive 1/2. So what's that going to become? It's going to become positive 1/4. So what we're going to get is, I'll just do some reorganizing now. Total height minus our initial height of our fluid is going to be equal to, like I just said, 1/2 minus 1/4 is positive 1/4. So we're going to have, I'm going to write the 4g on the bottom, 4 times the gravitational constant, just so I remember. And what we're going to have is the angular velocity squared multiplied by the total radius squared over the 4 times the gravitational constant. Now I can erase these. Then what was our question again? It was the angular velocity. What is the maximum angular velocity? So what we're going to want to do is isolate for this. So we are going to get that our a little too big. Our angular velocity. We're going to have a square root in here. Now, what are we going to have? So we want this. We're going to want to need to do is we're going to need to multiply by 4g up top. So we're going to have 4g, the total height minus our initial height of our fluid before spinning. Then we're going to have that over r squared. Is that correct? I feel like we're missing a term in here. No, no. So multiply by 4g divided by r squared. Oh, that's correct. And what we can actually do is we can do a little bit of further simplification. We could hypothetically pull out this 4 and make it a 2. And we can also make this an r and make that the radical exclusively up there. Okay. So through relating the pressure between radius and height, going further on, making the volumes equivalent, using that a few properties, the basic equation of static fluids, using these principles right here. Again, that's more of the volume kind of thing. What we've done is we successfully figured out the maximum velocity that a cup full of fluid could spin at a certain angular velocity. I thank you for watching, and I hope you enjoyed. Have a good night.